Yeah, I think we can begin. So today we're gonna be looking at infinite series once more. We're gonna be looking at this topic. We're gonna be looking at infinite series today. Uh, yeah. So on infinite series, I'd like us to begin with. We're gonna start from the back, right? We're gonna begin with root test. Usually, it's called the nth root test. It's called the nth root test. So when we come to the nth root test, let me do this. Let's see. Okay, my mic is on. So when we come to the nth root test here, we'll be using this test to check, just like we do on the ratio test. We'll be using this test to check. Can you, can, can you please mute your mic if you're not saying anything? Are you saying are you saying something, or I can't hear you? Let me just mute your mic. So that maybe you're not talking to us. So when we come to the nth root test, let's suppose that here you have this. Suppose that we have the series. Suppose uh, that we have the series, right? Then we're going to define, if we have this series, we're going to define our L being equals to the limit as n approaches infinity of the nth root of the absolute value of a of n, which will be equals to the limit as n approaches infinity of the absolute value of n, which is the same as this. So now, if we have this, then we know that the first thing that we check is if L is less than 1. If L is less than 1, then the series is absolutely convergent, right? Then we come and check if L is greater than 1, then the series is divergent. The third one, we come that say that if L is equals to 1, then the series may diverge. So here's what happens. The series may diverge. It uh, may be divergent, may be divergent or maybe conditionally convergent, or it may absolutely converge. May be absolutely convergent. So in other words, all this is trying to say that this is inconclusive. So when we say that it is inclusive, we're saying that it's possible that it may diverge, or it may be divergent, possible that it may be conditionally convergent, or it is possible that it may be absolutely convergent. You see, right? So that's the case. So now, did you guys do any proof based on this theorem, the root test? Did you do any proof? All right, means that we're also not gonna do any proof based on this. So now we come to questions, right? We'll come to questions. First, we are told to determine, we are told to determine if the following series is convergent or divergent. You see, right? Then the first one will be the summation infinity n equals to 1 n to the n over 3 to the 1 plus 2n. You see, right? So if we have this and we are supposed to check whether it converges or diverges, it means that we can use a root test for us to check whether it converges or diverges. So that's what we're going to do. So first, we must check L, the limit, right? We define that. So we're going to say L will be equals to, so let me write this with a different one. L will be equals to, we have the limit as n approaches infinity of the absolute value, or if you, or you can start like this, it's fine. N absolute value of, now we have n to the n over 3 1 plus 2n. You see, right? And this is equals to the limit as n approaches infinity of n to the n over 3 1 plus 2n to the 1 over n. So now if I apply that exponent on both the numerator and denominator, I will have, and the n will come and apply there. I'll have n, let me start by this, all over, if I just drop that, then this will be equals to the limit as n approaches infinity of n over 3, 1 over n plus 2. If I apply this n here and here, you see, right? And then when we see this, if I apply the limit here on the denominator, I'll get 3. This one will be like here, it will be like this. And then here I'll get 3 to the 2. And this is what? Infinity. And this is greater than 1. We're going to consider, always, we're going to consider infinity to be greater than 1. You see, right? Therefore, we can say so. We must specify by the root test By the root test, this series is divergent. You see, right? By the root test, this series is divergent. Now, can we check the second one? So if no question, then we can check the second one. Now we have B, we're given the summation n equals to 0, 5n minus 3n third, 7n squared plus 2 to the n. From here, we need to check the limit. L is equals to the limit as n approaches infinity of this nth root of 5 and minus 3n to the third all over 7n squared plus 2 to the n. Then this will be equals to the limit as n approaches infinity of 5n minus 3n to the third all over 7n squared plus 2n times 1 over n. So this will be equals to the limit as n approaches infinity of 5n minus 3n to the third all over 7n squared plus 2. Hmm? No, this one is to the third, Manish. Wait, did I copy a wrong question? So, according to the limit of this, you must know what is the limit of this, right? This will be, ish, I forgot the absolute value C. This will be, if we apply the limit, they will get minus 3 over 7. And this will be equals to 3 over 7, which is less than 1. And then we can say, so by the root test, you see, we had to apply an absolute value here for us to get this, right? Then we'll say by the root test, this series converges absolutely. This series converges absolutely. You see, right? And hence converges. So if it converges absolutely, then it converges, right? And then we are fine with this. So is there any question? Any questions, so we can go to the second one? So if we have no question, we can now go to the second one. We come and say we have C. On C now we have summation of infinity n equals to 1 over n squared. You see, right? Then we know that L is equals to the limit as n approaches infinity of n absolute value of 1 over n squared, which is equals to the limit as n approaches infinity of 1 over n squared to the 1 over n. And this will be, yes, root test. This one I'm doing root test. I'm doing only the questions that have to do with root test. Yeah, I'm just doing more questions based on root test. And then this will be n 2 over n. And if I apply the limit on the denominator, I'll get n to the 0. You see, right, which here is infinity. So what do you get for this? Will this will this give us, what will this give us actually? Not will this give us. What will this give us? What will be the solution if I have the limit of this? What what will be that solution? Eh? But what? Zero. Do you all agree on zero? Do you all agree on zero? It's one. How is it one? 20 by infinity to the exponent zero. All right. So here's it. Here's it. Yeah, I think I also agree on that one. So here's how the limit will be. If let me do this limit. Let's check. If we do the limit of n approaches infinity of n to the 1 over n, this will be, if you remember, if we plug, we're going to get infinity to the 0. What did I tell you if you get something like this? What do? You introduce ln, right? If you get something like this, you should introduce ln. So we're going to introduce e 1 over n ln n. Then this will be the limit as n approaches infinity of e to the ln n over n. Now if I plug infinity, get infinity over infinity. Now this is an L'Hopital rule. You see, this will be the limit as n approaches infinity. If I derive there, according to L'Hopital rule, get 1 over n, it's 1 over n, uh, e1 over n divided by 1. You agree, right? If I plug now infinity here, I'll get 0. And this will be e to the 0, which is 1. You see, right? So the denominator here is 1. So this will be 1. You agree, right? I was saying that if we have this ln of n to the 1 over n, if I plug and I get that, I get infinity to the exponent 0. You see, right now? This tells me anything that I get that is this, that like any kind of indeterminate form that I get in this format, whether it's this exponent, this one exponent, it tells me that I should introduce ln. You see, right? So now that I introduce ln, and now after introducing ln, I drop the exponent. So I can't introduce ln alone. You get it, right? I have to introduce e also. So I introduce e, then ln. I drop the exponent. I have ln of n. And then this was there on the test one. And then when you have this, now I know that I can take the ln to the numerator. Then now I plug again, it satisfies L'Hopital rule. You remember the L'Hopital rule of infinity over infinity? Now I can derive this individual. When I derive ln n, I get 1 over n. Derive n, I get 1. So if I apply the limit now, 1 over n, when we are approaching infinity, will be 0. So e to the 0 will be 1. You see, right? Then in a different case, if this is 2, 2, 2, 2, but still will still give us 0. You see, right? And then that will be e to the 1. Do you agree? Yes. So what you're going to get here, going to get the limit as n approaches Now I've already applied the limit. I'm going to get absolute value of 1 over 1, which is 1. And what do we decide on when we get 1? What do we say when we get 1? What do we say when we get 1? So by a root test, this will be inconclusive. You say right now, by a root test, this will be inconclusive. So we see now. Now let's come to another one. Then just since we have this, now we're going to have L is equals to the limit as n approaches infinity. What? Yes. Oh, when you say you have to say that by a root test, the series is inconclusive, then you go look for another test to solve that question. So this question you can just easily use p-test series. You say right. It converges by p-test series because p is greater than 1. Yeah. So this will be the limit as n approaches infinity of minus 1 n over n to the 1 over n. This will be equal to the limit as n approaches infinity minus 1 over n to the 1 over n. Already we know what is the limit of this one, the denominator. We agree right now. We agree what is the limit of the denominator. So it's 1, right? So this will be minus 1 over 1, and this will be 1. We agree, right? So you see that these two, they lead us to something similar, right? Which in this case also it will be inconclusive by this test, by the root test. So you would use alternating series to check or any series. So by the root test, this becomes uh, inconclusive. So by let me check. Now we can go to ratio test, right? So if you check by alternating series, this will converge if you use alternating series. So that is the case. Now let's see if we can go to the ratio test. Oh, is this pen? Okay, it's fine. Let me check. Let me see if I have questions based on. All right. So now I think we can start with alternating series. Since some say that we should do alternating series. Okay. So then after doing the alternating series, we can see which series are we going to touch. So now when we come to alternating series, let's suppose that we have a series an and either but this information is not. important that much. Yeah. Let's suppose that we have an, right? And this an should be greater or equals to 0. Uh, yeah. So if we have this, or let's say suppose we have an, the summation of an, and either, it's fine, let me just write it. An is equals to minus 1 to the n, and then let's say bn, and or we have an is equals to minus 1 n plus 1 times bn, or we can even have n to the, yeah, we can have to the n minus 1, anything on the numerator, you're on the exponent, and then where bn is greater or equals to 0 for all n. And then if the following conditions are satisfied, if we have the limit, we take the limit as n approaches infinity of bn is equals to 0, and we take the second thing, we see that a bn is a decreasing sequence, and then the series, that given series is convergent. See, right? So then that given series will be convergent. And then now we can try to look at some questions. So first, let's look at simple ones. We have the first one. They say we should determine. They say we should determine. Um, we should determine if the following series is convergent or divergent. Then the series is as follows. Then for us to check using this alternating series, we can first note that we can write this in this format. We can write this in this format. You see that we can write it in this format, which in this case would mean that our bn will be equals to 1 over n. You see right? Which this would mean that our bn will be 1 over n. Then first, we check the limit as n approaches infinity of 1 over n, or of bn, which is equals to the limit as n approaches infinity of 1 over n, which this will be equals to 0, right? And then secondly, we check whether this is a decreasing sequence or not. But we know that for all n, n will always be equals to n. So this is how we're going to start, right? For all n, n will always be equals to n. So this is where we should arrive. If this is a decreasing sequence, a of n, a of n, let me say, not a of n, let me say b of n, which is equals to 1 over n, should be greater than 1 over n plus 1, which is bn plus 1. For this to be a decreasing sequence. So this is where we should arrive. And we realize that on the other side, here we have n, here we have n plus 1, means that we can add n plus 1 on the other side. This would imply that n, if we add plus 1 that side, this will become less or equals to. So, and here will imply then, or not even equal or less to, I can even say, since this is correct, This will imply we realize that we must inverse both sides. Now I inverse this will change 1 over n plus 1. And this will imply we know that this one is bn and this is bn plus 1. Then this is how you're gonna check. That's why I decided to do this question. Majority were asking me how can I show this? If you just come and write this, you're missing out. You didn't show. So should be careful of that. Now, now let's come to deduce. Is this convergent or divergent? Does this converge or diverge? It converges, right? So it means that you are going to say since both conditions are met, so by alternating series, test the series converges. You see, right? So now we know that by alternating series, this will converge. Then now let's come to the second question. Now, when we come to the second question, we have the summation of from 1 minus 1 n squared over n squared plus 5. Then we know that we can write this as minus 1 is to the n squared over n squared plus 5. Given that bn is equal to n squared over n squared plus 5. Now we check the limit first. We check the limit. N approaches infinity of n squared over n squared plus 5. This is what? 1. You see, right? Now we realize that, okay, let me write this. Notice that this is equal to 1. And this one is not equal to 0. There's no need for us to continue check the second condition. Therefore, we say that since the limit or the first condition is not met, this pen. Let me plug this pen. I think it's giving me problems. Yeah. So since the first condition is not met, then also we say that since that first condition is not met, so we can say that the series, so by alternating series just the series diverges. You see, right? Then that will be the case. So I'm sure I've showed you there how do you apply this thing. So let's come to this one now. This one question. See, we have now this n equals to 2 over cos of n pi over root of n. So Now they ask us, is this convergent or divergent? Now if we check cos of n pi, this will revolve around -1 and 1. So it's the same thing as coming to replace that. We can still replace this as this. You see, right? Times 1 over root of n. Given that bn will be equals to 1 over root of n. You see, right? Given this. And how did I decide to replace that by -1 to the n? If I plug 2 here, what do you get if you plug 2 on cos that? You get 2 pi, right? So take 2 cos of 2 pi. What do you get? Do you get positive or minus? Cos of 2 pi using radius. Hmm? What? You get positive. So it means that if I take this 2 and plug here, I'll get positive. You agree right now? But if I got negative, I would come and do plus 1 here so that when I plug 2, I get negative. You see, right? So that is the case. Is there any question? If not, then we can proceed, right? Then first we check the limit as n approaches infinity of bn, which is equals to the limit as n approaches infinity, 1 over the root of n. What will be the limit of this? 0, right? Then we know that this is what we must show now. For the second condition, this was the first condition. For the second condition, we must show this. We must show that bn, which is equals to 1 over the root of n, is greater than 1 over the root of n plus 1, which is bn plus 1. You see, right? For us to show that, we must come and say for all n, we'll always have n being equals to n, which this will imply on the other side, we see we have plus 1, n will be less than n plus 1. And this will imply that we have root both sides, then we can root both sides, we root both sides. Then now we flip. This will imply that we'll have 1 over root of n, which is greater than 1 over root of n plus 1. So this will imply we know that 1 over root of that is bn, so greater than bn plus 1. You see, I've shown that this is decreasing. Then we are good to go. All right. So if this is the case, that means that now we can say that since the two conditions are met, then the alternating series will be convergent. Do we agree? All right. So for the alternating series, we can move. Now let's say I see on tutorial 7, they said we should determine whether the given series converges absolutely or converges conditionally or it diverges, right? So the question with you, I know that someone's asking, what do we mean when something is converging? Converging? Absolutely. We know that one well. Then what do we mean when we said converges conditional? So to give a definition for that, we can say that if we have a series of A of n, and this series is called absolutely, this series is called absolutely convergent if, check, if the summation of this, you said that name, is convergent. You see, right? Now that one is called absolutely convergent. This one is simple. We've done it. Then now we say that now we say that if the summation of an is convergent and the summation of this absolute value n is divergent, we call the series to be conditionally convergent. If you take the normal series, you find that it is what? It is convergent, but its absolute value series is divergent. Then you can tell that that series it is conditionally convergent. Now, for example, let's look at this one. We have the summation of infinity n equals to 1 of minus 1 to the n over n. Then we realize that if we use alternating series for this, if we use let's use alternating series, we know that by alternating series, right? By alternating series, if I take that and write it like this, right? And then I have my Bn is equals to 1 over n. Then I say the limit as n approaches infinity of 1 over n, this will be 0. You agree right now? This will be 0. And then we say that this is the first condition. We say that if I have for all n, we know that n is equals to what? N. And n will be less than n plus 1. And then we have 1 over n is greater than 1 over n plus 1. By alternating series, this would converge. You agree right now? By alternating series, this would converge. But also, if we check this, we know that this one, if this is by harmonic series, it would diverge. Do you agree with me? Now let's do this. This thing, the series first converges, and the rule says what for conditional? It says that if this series is convergent, now let's check the absolute value. Let's check its absolute value. Then we come. Now we know that therefore, I'm not gonna write everything. I'm just gonna write the series converges by alternating series, right? But if I take the absolute value of that series, you see, right, minus 1 to the n over n. If I take the absolute value of this series, I'll have 1 over n. And this series diverges by harmonic series or yeah, by p test. Can be a harmonic series or by p series test. You see, right? So the original one converges by alternating series, and the absolute value one diverges. You see, right? So if this is the case, then we say hence the series is conditionally divergent. You see, right? Then since we took this example, we can now look at the questions on the you as did I say divergent? I didn't see. There's such a thing doesn't even exist. I didn't see. Thank you. Convergent. So we come to tutorial 7. Now from tutorial 7 we have A, we have K is equals to 0. Then we have minus 1 to the K over K squared plus 4. Then from here we see that we can even use alternating series. You see that by alternating series this will be K equals to 0 minus 1 to the K times 1 over K squared plus 4. And if we say now that Bn, which this would imply that Bn is equals to 1 over K squared plus 4. Then if we check the limit of Bn, Bk is not Bn. We check the limit of Bk, we'll have 0. You see, right? And then secondly, we say for all n, we'll have that n is equals to n, and we'll have that n is less than n plus 1. You see, right? And this will imply if we have both sides not n minus k, why am I always using n? We know that this is what we must show. Usually I like to write what I must show so that I don't forget, right? So that bk, which is equals to 1 over k squared plus 4 is greater than 1 over k plus 1 squared plus 4, which is equals to bk plus 1. So already I know that I have k plus 1 on the other side, which I did write k plus 1, and I know that this is squared. Then after, we add 4. Hey, look, what I'm doing. I squared the wrong thing. Then I add 4. This will flip now. I'm sure you guys did consult about this, right? You should consult. It's very important to consult if this guy still allows this method that he showed me last year. So you should consult and check that. So we realize that, okay, for this one, this is the case. You see, right? So do we agree? All right. So now we found this and we know that since both conditions are satisfied or are met, so by alternating series test to series converges. So we're not done, right? we checked the normal one, then now we check its absolute value. So that's what they're trying to tell us when they ask us, is it conditionally or you see right? That's 1 to the k squared plus 4. So we get this, right? Then the question is, will this converge or diverge and by which test? Will this converge or diverge and by which test? It will what? It will converge, right? Also by comparison test, we're going to get that P by P series test, 2 will be greater than 1, right? So you can use the following. You can use integral test. You can use ratio test. You can use, what was the other one? Yeah, he said comparison test. We can also use the limit comparison test, right? Yeah, we can use this. So, but yeah, you can use any of this. But what I know about the root test would give us inconclusive. I think also this one might give us inconclusive. You must be careful of this ratio and root test. Must be careful. So we see that now, if we use integral test, there we are going to get that one is convergent. So if we get that it is convergent, it means that this thing is what is absolutely convergent. You see, because they wanted us to check whether this is the question. And they want us to check whether this is absolutely convergent or conditionally convergent or it diverges. So we realize that here, since this one of the absolute convergence means that it is absolutely convergent. You see, right? But if we found out that it was divergent, we would say that this is conditionally convergent. You see, right? Because the normal series converges and the absolute value series would diverge. Are we fine? Think if we are fine, we can proceed. Yes, 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 yes. Mm. Does it matter whether our case starts from 0 or 1? You said if does what? Yeah. Oh, yeah. Usually, the p-test series applies when we are starting from 1, right? Ne? But if even if we start from 0, uh, those limits from 0, they will just give us certain constants that won't affect us. You see, right? So it won't matter. We can still analyze it from 0. Yeah. So, but it will depend. It has to depend on what's this? It has to depend on the function. But it's much better when starting from 1. Because if it starts from 0, you can still do this. Let me show you something. If you have, You can still say that this is 1 over 4 plus, you see right there. Then you apply the P series test. I think you guys can do this so that things become simple. You see right? So you don't get penalized. You can still do this. You apply it from your one. Is that fine? All right, no problem. So now I think let me check which. Okay, I think we'll still do. Yeah, this one I think we said that it will be uh, absolutely convergent. So now we ask ourselves, should we do the I think, do you guys are you guys fine with the integral test, or should we do it? We can do the integral test, right? All right, all right. So now I think when we come to the integral test, let me see. Yes, yes, yes. 2005. Uh, yeah, I think based on time, we can't be able to go through. But I'm just one. Promise we can't be able to go through the tutorial. So I'm just taking few questions, this and this and this. I think what you can do, you can just write questions which you want to write, and then you send in the group. Then we'll look at them. You see, right? And then you just write in the, or maybe ask any question in the group if you want. Cool. I think we're left with uh, 13 minutes. And then now I'm told to do integral test. Is that fine? All right, all right. Yeah, you can just do them while we'll be looking at them in the group. So when we come to integral test, right, there are certain conditions that we look at. We don't just apply the integral test. If we come to integral test, we should be sure that whatever function that we're dealing with, let's say I'm given, let's say an example. If I'm given the summation of, can I say what's the summation of? Let me take this one. Summation of k equals to 1 of 1 over k squared plus 4. If I'm given this, right? So if I'm given this, I'm going to let f of x be equals to 1 over x squared plus 4. You see, right? And then when I let this, I should be sure that f should be 1, should be positive, and we are certain that f is positive, right? 2, continuous, and the 3, f should be decreasing. So it should be continuous within this interval 1 up until infinity. So if I plug these values 1 up until infinity, we realize that uh, we can't get any undefined. You agree right there? So it means that this will always be continuous there. So for this function, it will be, because now I want us to check whether this thing, I want us to check if this thing, you said that it will converge, right? So I want us to check it using integral test. So from this example, mm, so from this example, we realize that this is positive, f is positive, and f is continuous. And the question is f decreasing? Can we do we say f is decreasing here? Do you agree that f is decreasing? Is it decreasing or increasing? It's decreasing, right? Yeah. So you can check whether it's decreasing or increasing. You can use any method to check that, right? You can also use the ones which I was showing you. You just consider this as a of n. You check if it's gonna be decreasing or increasing. So, but we have checked that using the alternating series there. We check that indeed that function is decreasing. You see, right? So we know. Now, since it is clear that it is both positive, continuous, and decreasing, then now we can use the integral test. We can now come and write this from the integral test of 1 over x squared plus 4 dx. You see, right? And this will be equals to, we apply now, we check. If I plug 1 here, this will be fine. So I'm applying the improper integral. If I plug 1 here, this will be fine. But if I plug infinity, it will be undefined. So I must replace infinity. You see, right? So I'll replace infinity. Then I'll have 1 over x squared plus 4 dx. So now the question is, how am I going to integrate this? Who can tell us? How can we integrate this? How can we integrate this function? Use what? Use substitution, right? So it's saying that we can use substitution. Do you, is there anyone who agrees or disagrees? It's saying we can use substitution. Do you agree or disagree? Do you agree or disagree? Hmm? So you agree, guys? Guys, do you agree or disagree that we can use substitution? Yes or no? All right, but while you're still thinking, yeah, we're gonna use the inverse of tan. So we can, yeah. So, cause the reason being, guys, check if you let u be equals to x squared plus 4. U substitution has rules. If I derive this, I get 2x dx. The question is, will this 2x cancel anything here? No. You see, right? So U substitution fails. It can't cancel anything. So we can't use the substitution. You now see the idea right now. So it means that we must come and use the inverse of tan. So here's what the inverse of tan says. I'm going to just give you a rule. It says that if we have the integral of 1 over x squared plus a squared dx, this will be equals to 1 over a arctan of x over a, over this inside over this one. You see, right? And then in this case, we have, this would imply that the limit as t approaches infinity of 1 to 1 over x squared plus 4, which in this case 4 is 2 to the exponent 2 dx. You agree, right? This would be equal to 1 over what? 2. Our a here is 2. You agree, right? Arctan, our x, we have x, our a is 2. We have this. Do you now agree? So we put this. This is 1, this is 2. You see, right? And this would be equals to, now I substitute that, I only have the arctan over t over 2 minus the arctan of 1 over 2 all over 2. And then ish, I forgot to write the limit. Also, here I forgot to write the limit. Oh, that's fine. Arctan T over 2 minus arctan 1 over 2 1 over 2 1 T. Eh? No, ish, I skipped it that step. Why am I skipping step? I wanted to write that one. Again, we said that that would be 1 over 2 arctan x over 2, right? 1 T. Then I can write that one here. With the limit as T approaches infinity of the arctan T over 2 minus the arctan 1 over 2 all over 2. We agree here, right? Then that will be the case. Now, the next question that we can have now is what is arctan minus 1 over 2? Can we check what is arctan minus 1 over 2? Oh, what is arctan minus 1? Oh, what is arctan 1 over 2? What is arctan 1 over 2? Arctan 1 over 2? Hmm? Guys, what is this? I don't have a calculator next to me. It should be a calculator. Uh, People are not answering now. Wait. Do you guys even have calculators there? What is arctan 1 over 2? Oh, the original question here started from 0, right? I took the wrong one. This one starts from 0, 0, 'Yeah, I think if it's 0, we don't even have to know what is there. That will just be. Is it fine now? Oh, ish. Who's, who's having their mic on and there's noise, guys? Yo, kusia. Then stress. So now, yeah, I'll say that I had taken this one by mistake, right, of 1. I'm doing this one of starting from 0 because we want to see really see if this one is convergent or not. So if it starts from 0, I don't have to ask myself what is arctan, whatever. So I just know that arctan 0 will be 0. So this will be the limit as t approaches infinity, t over 2. And if we plug this here, Here's what you should know. Another thing that you should know is that if we have the limit of arctan t, this will be, what should be the solution here for arctan that? What should be the solution if we are approaching infinity? This will be pi over 2, right? So you must try to check that. That will always be pi over 2. If we have this, that will always be pi over 2. Or we can even say it like this. Maybe we say arctan of infinity. This will always be pi over 2. Do you agree? So if we were all agree, yeah, this is what you should just know. The arctan of that will always be 1 over pi over infinity. So it means that your pi over 2, man, that will always be pi over 2. So it means that this will be pi over 2 over 2, and this will be pi over 4. You see, right? So it means that since this is pi over 4, therefore we know that the integral, or not the integral converges. Then the series also converges. You see, right? So always keep this in mind for the integral term. Hmm? Let me check. Yes, it's pi over 4. Yeah. So now, do you agree? So it means that I think we've come to the end of the session.